Hello everyone, I'm Davide Maddaloni, and I'll be presenting experimental investigation of space plasma thrusters via data-driven analysis techniques under the supervision of Drs. Mario Mirino Martinez and Filippo Terragni. So, the motivation behind this is that plasma oscillations are a wide range of topics spanning from different fields such as electric propulsion, what we're doing, fusion reactors, astrophysics, and more. The role of plasma oscillations the interest in plasma oscillations is actually rising since it has been shown that they can actually impact propulsive performances by enhancing transport. One example is anomalous transport in Hall-effect thrusters, which is basically one of the main topics nowadays that are still unresolved. My thesis basically will be mainly focusing on two different thrusters, which is the Hall-effect thruster here and helicon plasma thruster, which is a different technology that uses magnetic nozzle, which is a completely different type of thruster. To date, the oscillations are mostly better characterized in Hall-effect thruster since it's a more mature technology, whereas the oscillations in magnetic nozzles are far less characterized since they are a newer technology in general. So the way we are approaching the problem is by using data-driven algorithms to try to dissect the physics of these oscillations. Dealing with data in general can be difficult because of noise, dynamic superposition and interplay, and the common problem of researcher bias. Data-driven techniques are a versatile and powerful tool that is emerging in the last decades, I guess, that can help the research to extract meaningful features that are hidden in the data. One of the techniques that we have been focusing the most during the last year is the 2 points cross power density technique, which is basically taking into account the fact that, like, if you have a wave, imagine this wave is traveling and you can collect this signal by means of two different probes. This wave will be gathered by the two probes in two different instants, and if the wave is traveling, the two signals will have a difference of phase between them. You can recover this phase difference by computing the cross correlation of these two signals, which is going to be a complex number that has real and imaginary part. The imaginary part is related to the phase difference of these two signals, and this phase difference can be used to compute a local wave number, which is an estimation that under some hypothesis approximates well the actual wave number of your oscillation. You can also provide scaling depth by computing the real part of the cross power density, which tells you basically how much power there is. The experiment we have done is by placing our probe system of 3 different Langmuir probes into the magnetic nozzle of the helicon plasma thruster, one of the prototypes that we have in the AP2 lab, by using a rotating arm that moves in a sort of like circular direction, and that allows you to resolve basically 2 different directions: the direction D, which is the direction approximately parallel to the magnetic field, and the one perpendicular to the magnetic field here. This way, you can characterize spatiotemporal oscillations in the plume, and that allows you to resolve them. You basically gathered time-resolved measurements and time-averaged measurements of the plasma. Within the plasma, the time-resolved measurements have been gathered at 3 different distances: 50, 100, and 150 millimeters. And each of them has 10 different angles at which we have moved the arm, so that we can characterize basically the plasma at these 3 different distances at 10 different angles. We have been also changing the mass flow rate of the thruster so that you can characterize parametrically what's going on, but this presentation will be mainly focusing on the nominal operational regime. We also have gathered time average measurements to help characterize the main parameters of the plasma, so that you can have something to dissect the physics behind. The time average measurements allowed us to recover plasma density, plasma potential, electron temperature, and magnetic field. That are the main actors of whatever drift is happening in your plasma. In particular, the main two drifts, the order one drift that we are focusing on are the E cross B drift and the diamagnetic drift. Where like the Kn here is basically the characteristic length, 1/length of the gradient of density. These are the main two drifts that we are now focusing on, the order ones, and usually drifting plasmas are frequently unstable. So, and this is like something related to how much our estimations of these velocities are in the three different distances, or 50, 100, and 150. One of the positions, like 100 and alpha equal to 30 degrees, shows basically that there is a prominent broadband oscillation in the theta direction, in the negative direction of theta, whereas there is a small or non-existent component in the axial direction. You can also see that by looking at the power here, there is a power bump for the azimuthal component of the power, whereas this bump is not as much prominent in the axial direction. We have again computed the local wave number that I introduced before. We can also compute power. This plot shows also the power, and basically, yes, this bump happens more or less around 50, 60 kilohertz. And if you compute basically the phase velocity of this curve, you get something roughly in the range of 10 to the 3, 10 to the 4 meters per second. What happens is actually coherent with like the results that you see at other points in the plume. This is at 35, same distance, and this is basically at the same distance, but at lower angle, like 20. The fact that like this oscillation is triggered by moving away from the central line suggests that this oscillation may be triggered by gradients. And for some configurations, you see here there's again the power bump around 50 kilohertz, whereas here the power bump at 50 is not visible, but there is another small power bump here around 100. Which basically happens to be in the region where the slope of this curve changes. You see that there's a different behavior, sort of different behavior, below 100 kilohertz and above. Whereas if you move with the distance, what you see is that at higher distances, the behavior is conserved. There is still like the left Y strand in the negative theta direction. There are not any more strong bumps in the power distribution. Whereas at the closest distance, you do not see the slope as much, which means that something is preventing this oscillation from developing at that distance fully. But you can see if you increase the angles that the behavior above the 100 kilohertz is starting to develop here. Ongoing is to try to justify this oscillation by computing an analytical dispersion relation. Some ideas include like gradient-based drift and anti-drift waves, such as, again, diamagnetic and E cross B drifts. And we have also read something that talks about drift magnetosonic waves. The problem is that the literature that nowadays talks about some results that are comparable to ours do not univocally agree on the source of this oscillation, two of the main ones shown here. As soon as we have something to explain this, we are planning to release a journal paper based upon these results. In the future, we are planning, like a research stay could open up possibilities for follow-up possibility for new line of research or follow-up existing ones. And then after that, I will be writing my thesis. Performance activities include one conference contribution in 2021, one journal paper that has already been published, one participation to a workshop. And these results will actually be presented in a conference now in July at ICPIC in the Netherlands. And again, we are planning to announce a paper based again upon these results. Thank you for your attention. And if you have any questions.